in the last lecture, we attempted to provide an overview of Riemann integration. The emphasis was for some limitations of Riemann integration. Though Riemann integration is simple, elegant, first systematic study of integration, it has some deficiencies, or at least certain things we would like to happen in integration does not happen in Riemann integration. I have given a few points and example to corroborate those points. These deficiencies of Riemann integration made Henry Lebesgue to revisit Riemann's approach of integration. Let me remind you once again the basic difference between Riemann integration and Lebesgue integration with a simple example. I have done this previously as well, but this is just to recall. Let us take a step function. Consider a step function. Let us say defined on closed interval 0, 1. So the domain is closed interval 0, 1. And you are considering a step function. Let us say the function assumes 4 different values. Alpha 1 on the interval I1, alpha 2 on the interval I2, alpha 3 in the interval I4, I3, and alpha 4. In Riemann's approach, if you want to find, this is your function f of x. Integral 0 to 1 f of x dx, which is area under the curve f of x between x is equal to 0 and x is equal to 1. You can see that that area will be sum of areas of 4 rectangles with height alpha 1 and width length of the interval. So this is alpha I into length of II, and do it for each subinterval. This is what Riemann's integration is as far as a step function is concerned. What Lebesgue did is the following. You consider the range set, the values taken by the function. And this particular example, the function takes only 4 distinct values, namely alpha 1, alpha 2, alpha 3, and alpha 4. And looking at the range, you divide the domain. To be precise, you consider inverse image of these distinct values, f inverse of alpha I, okay, and multiply the distinct values the function takes, namely alpha 1, alpha 2, alpha 3, alpha 4, with the length of sets which are inverse image of these values. Okay. So look at the range. There are 4 different values, alpha 1, alpha 2, alpha 3, alpha 4. You consider F inverse of these. These F inverse of alpha I will be the subsets of the domain. You consider the length of that, okay, and then multiply with the distinct values assumed by alpha I. Okay. This is integral 0 to 1 fx dx. This is Raymond's approach, first one. And the second one is Lebesgue's approach. The basic difference is that Raymond's approach subdivides the interval, the domain, into several subintervals. Whereas Lebesgue subdivides the domain looking at the range. You consider those values which are distinct and then consider F inverse of those. If instead of this step function, you have an arbitrary function, and if you consider F inverse of alpha I, that need not be intervals. It can be some subset of the domain, which is not an interval. And therefore, Lebesgue approach will force to define length for sets other than intervals. This F inverse of alpha I in this example happened to be interval, but that is not in general. Okay. Therefore, Lebesgue started by studying length for arbitrary subsets of R. To be precise, a generalized version of length for arbitrary subsets of R. And he called it measure. Okay. And that was the starting point of the rigorous measure theory. Therefore, this example should remind you not only the basic difference between Riemann and Lebesgue's integration, but also the fact that Riemann integration divides the domain into intervals, and for intervals, you already know a measure, namely the length. However, Lebesgue's approach of integration forces us to divide the domain into subsets other than intervals. And therefore, we want to talk about length for subsets other than intervals. Or we want to generalize the concept of length so that you can talk about length for subsets other than intervals. And that generalized length is the measure. Okay. So this is what we were talking this for the past 2-3 lectures. Now, how do you define measure? Is the question. Okay. So far, so good.
Yes, sir.
Okay.
Yes.
There are several ways to define measure, and you have already seen the most abstracted version of measure. What is it? Okay. Given a non-empty set omega, what is a measuring system? By a measuring system, on omega has basically two ingredients. One, a suitable collection of subsets of omega. Okay. And that suitable collection is actually the sigma algebra. A collection B of subsets of omega. That's, in fact, B is a sigma algebra. That is the suitability. We have seen it. And the second ingredient is a function mu from B to R star, which is R union infinity. In fact, you can say closed interval 0, infinity, infinity included, satisfying certain axioms or properties. So these are the two basic ingredients for a measuring system. Now let us take omega to be R. Let omega is equal to R. What we are looking for, or what Lebesgue looked for, is a measuring system on R that is consistent with the length. Okay, we have the notion of length for intervals in R. For the future reference, let me introduce a notation. Let script I be the collection of all intervals. In R. So for each element in script I can talk about a measure, namely the length. Okay. Our aim is to push it further. We are looking for a measuring system or a measure on omega is equal to R that is consistent with length. What does it mean to say a measuring system that is consistent with the length? That is, we need three things. A sigma algebra B. That is, we are looking for a sigma algebra B of subsets of R. 2. A function mu from B to 0 infinity such that, let me write it explicitly, such that 1, mu of null set is equal to 0, and 2, mu of union En is equal to summation mu of En n in n for a countable collection En of disjoint sets. So let me repeat. We are looking for a measuring system on R that is consistent with the length. Meaning, we need a sigma algebra. We need a function mu satisfying three conditions. One is non-negativity that I have included here by saying mu is a function b from 0 to infinity, and it satisfies these two conditions. Now, what This tells you that we are looking for a measure. Now, what do you mean by you want measure to be consistent with the length? Meaning, this sigma algebra that you are looking for should contain script I, the intervals. Okay. P contains I. And further, the mu of any I should be equal to length of I, and this should be true for every I in script I. This is what we are looking for. Such a mu we are looking for. Is it okay?
Yes, sir.
Now let me tell you intuitively what Lebesgue did. What Lebesgue, how Lebesgue pushed the idea of length to arbitrary sets, which I hinted in the end of the last lecture. Okay. So if you are in I, if your world is script I, no issue. You already know a concept of measure, namely the length. Okay. Now let us consider E subset of R, and suppose E is equal to union IN, N belong to N, INs are disjoint. INs are disjoint. Okay. You are looking for a measure, and you are looking for a measure consistent with the length. Take these two conditions together. So I don't have much freedom to define mu of E. Since E is union N belong to N IN, mu of E I should define as summation N belonging to N mu of IN. And since INs are interval and I am looking for measure consistent with the length, mu of IN I should define as length of IN. Therefore, though explicitly we are saying that we know measure only on script I, in fact, we know measure not only on script I, but on a larger subset. Okay. So that larger collection I will call as, let C is equal to collection of all E subset of R. E is equal to union N IN, IN's disjoint. Now, if you pick an E from C, I know how to define mu of E. So, every elements in script C are now like standard objects. I know how to measure them. Something like rectangle or whatever it is. So, whenever you pick an element from C, I know how to measure them. So, they are like a standard object in geometry. Now the next step. So from intervals, we went up to union of disjoint intervals. Now suppose E is a subset of R. Now let me complete this. For any E in script C, we know how to define mu of E. Okay. The next level. Now suppose E is a subset of R. Now let E be a subset of R, and E is equal to union of Jm. M belong to N. Jm's intervals. Jm's intervals. I don't know whether it is disjoint or not. As I told you, then this E can be written as union of disjoint intervals. Okay. E can be rewritten as E is equal to union in, n belong to n, in's intervals and in's disjoints. And therefore, I know how to measure E. And therefore, mu of E is equal to summation n belonging to n in. Therefore, the class of subsets of R for which now I can define measure is being slightly pushed further, slightly extended. Okay. Now let me consider let C dash is equal to collection of E subset of R. E is equal to union Jn, n belong to n, Jn's intervals. Now, for any E in C dash, we know how to define mu of E. So from script I, the length of each element in script I, we pushed our measuring facility up to C dash. Now I can define any subset of R which is union of intervals. At this juncture, as I hinted in the previous lecture, you can recall the so-called Lindelof theorem in real analysis, which reads as follows. Every open set in R can be written as countable union of disjoint open intervals. Okay. Recall that every open set in R can be written as countable union of disjoint open intervals. And therefore, every open set will be an element in C dash. And therefore, we can measure open sets. Okay. Thus, if O subset of R is open, then O is in C dash, and we know how to define mu of O. Starting from length of interval, we went up to measure or length of open sets, generalized length for open sets. So we have expanded the world of measuring sets in R, the sets which can be measured in R. So we are reaching up to open sets. Now, next level. Next, for E subset of R, any set, I can always find an open set enclosing this E. Find an open set G such that E is contained in G. This is always possible. At least you can take G to be equal to R itself, and R is open in R. Okay. And since you know how to measure G, G being open, I know what is mu of G, and that mu of G can be treated as an overestimate, an estimate from outside. for measure of G. Okay. We know how to define mu of G. And this will provide an overestimate for the set which you wish to measure, namely E. So I would write measure of E. For measure of E. So now the question is the how to get a best overestimate. Okay, so consider the best overestimate, and that can be treated as measure of E. Okay, so what will be the best overestimate? What did you do? Given a set, you put it inside an open set, and then you consider the measure of the open set, because I know how to measure open sets. Okay, so if you want to have a best overestimate, what should I do? Can somebody tell me?
So it should be the smallest open set containing E.
Or in other words, what you can do is you take
Infimum of
the,
Infimum.
yeah, you take the open set
yes.
containing E, measure it, and then find the infimum. Okay, so find infimum of mu of G, right? What is G? Where G is open, G contains E. G is open and G contains E. Can be treated as the quantity, this can be treated as best overestimate. And this is defined as this best overestimate. These are all in layman's language. Okay, best overestimate is defined as measure of E, mu of E. So this is the definition. So if you want to get measure of an arbitrary set in R, you take measure of an open set containing that set and take the infimum, where infimum varies over all open set containing E. But whenever you, so this is G is like a cover. Okay, it covers E. Whatever you can do with an open set, whenever you can cover with an open set, you can cover it with open intervals. So instead of working with arbitrary open set G, it is enough to take open intervals INs, which covers E, whose union covers E. Okay? So that is the starting point of measure theory, and that's what Lebesgue defined as measure of a subset of R. Okay, so with all these intuition and layman's understanding in hand, now let us precisely define what is outer measure. This measure is called the outer measure, and the reason is clear, because you are measuring from outside or you are measuring externally. Okay, so with all these things in hand, now let us go to the precise definition of outer measure. And the starting point is interval. Okay, so I shall start by defining the length of the interval. Just for the notation, I will make it more precise. Lebesgue outer measure. So let me start with the definition. This is more than a definition, it is notation. the length of an open interval I denoted by L of I is defined as follows. Length of I is equal to B minus A. If I is the open interval AB, A and B are real numbers, and A less than B. And I will define it to be 0 if I is null set. I will treat null set also as an open interval. For instance, A comma A comma B with B equal to A. And I will define the length to be infinity if I is something of the form minus infinity A or A infinity for some A in R. To handle the infinite intervals. And also, I will define it to be infinity if I is whole R minus infinity, infinity. Okay. So this is my definition of length for an interval. Now, similar definition will apply for closed intervals, semi-closed, semi-open intervals, and so on. Okay. Now, with this notation in hand, let us define Lebesgue countermeasure. Let us start with a subset E of R or A of R, whatever it is. The Lebesgue outer measure briefly we may call just as outer measure of a set A in R is given by, who can define it for me? Those who have read from book, don't tell me. With the things that I have supplied, if you can guess, it will be nice. Is given by the Lebesgue countermeasure of a set A in R is given by, the notation is this, okay? M star of A is equal to, yeah, who can define?
Infimum of G where
What I should do, I should find an open set covering A. But I told, instead of covering A with open sets, it is enough to cover A with the union of open intervals, right? So, and once you have union of open intervals, the measure of that will be the sum of the length. So you take it as, you go back and see this. Yeah. So you want mu of G, where G is open and G contains E. But now instead of an arbitrary open set and covering E with the arbitrary open set, I am going to cover E with union of open intervals. Okay. And therefore this mu of G will be sum of length of individual intervals in that covering. So my definition would be summation length of In, n is equal to 1 to infinity, where INs are open intervals such that what should these ions do? A should be contained in union and ion.
Union.
This union and ion. And you should do this for each and every possible covers of A and then take the infimum. So this is the definition. Infimum of summation L of ion, where ions are open intervals such that A is contained in union ion. I would call it as a cover. Okay. So for each set of reals, what I should do, I should consider countable collection ion of open intervals that covers this set. Okay. And once you fix a collection, for each of the elements in this collection, I should find the length and then I should sum it. And now do it for each possible cover. That's what I have to do. And then take the infimum. Okay, this is the definition of Lebesgue countermeasure. Now let me give a few comments here. Why I should consider only countable cover? Why not finite? That is just for a notational convenience. Finite is obviously included there. Okay. If you can cover A with I1, I2, I3, etc., IK, I can again say that A is covered by a countable collection with IK plus 1, IK plus 2, etc. as null set. That can be always done. So just for uniformity, we will always say that we are considering a denumerable or countably infinite collection of intervals. But finiteness is included there. Okay. So that's the first comment that I would like to make. For notational convenience, we shall deal only with countably infinite. Only with or denumerable. Countably infinite coverings of A. By cover, I mean this. A is contained in union ion. The finite case is included here. Since we may take ion equal to be null set. Remember, null set I have considered as an open interval. Null set except for finite integer. In that case, in the finite case, you can consider ion to be null set except for finite. Okay. Another thing that I want to draw your attention to is the following. When I say open interval, remember the intervals of infinite length is being considered, can be included. For instance, minus infinity A, minus infinity, infinity, etc. are considered. Okay. Therefore, length of this ion can be infinity for some ion. In that case, summation length of ion will be considered as infinity. Okay. So this is actually, this definition actually involves a series. Summation n equal to 1 to infinity L of ion. But unlike the usual series in real analysis, where we talk about convergence only when the limit is finite, here we can include the infinity case as well. So let me make it more precise as follows. The definition of outer measure involves a series. involves an infinite series. If you see infinite series of positive terms, okay. Now, the infinite series here, this is the convention we follow. Summation Tk or Tn, n is equal to 1 to infinity, of a sequence Tn, n in n, of, here Tn's are elements in 0, infinity, of elements in 0, infinity, infinity included. If you see it, it is summation L of In. This L of In can be any non-negative real number and it can be infinity as well. Okay. So we are dealing with series of the form summation n equal to 1 to infinity Tn, where Tn's are elements in 0, infinity. So the infinite series of sequence elements in 0, infinity is defined to be, so what is summation? It is defined to be plus infinity if some Tk is infinity, some Tn is equal to infinity. Otherwise, suppose no Tn is infinity, otherwise summation Tn, n is equal to 1 to infinity, is as usual defined to be the limit of sequence of partial sum, the limit of increasing sequence S1 is equal to T1, S2 is equal to T1 plus T2, S3 is equal to T1 plus T2 plus T3, and so on. The limit of partial sum. Okay, that is what is defined as the summation. Summation n is equal to 1 to infinity Tn is equal to summation n is equal to 1 to Ktn. This is as Sk, kth term in the sequence of partial sum, and then make limit k tending to infinity. What I wanted to say explicitly is that when I say this limit, I am including plus infinity as well, possibly plus infinity. This limit can be infinity. That is, this sequence of partial sum may diverge to plus infinity. In that case, I will consider this summation to be plus infinity. Okay. So if one of the Tn is plus infinity, then I will consider summation Tn to be plus infinity. And if none of the Tn is plus infinity, then I can take sequence of partial sum. If the sequence of partial sum converges to a finite number, then that finite number will be summation Tn. If the sequence of partial sum diverges to plus infinity, then that plus infinity will be considered as the series. This is slightly different from the usual series that you deal in real number system, because we are including infinity also. Briefly, we are in extended real number system. So this is the definition of Lebesgue countermeasure, and these are the few points that you should keep in mind. One is that enough to deal with countably infinite cover. And second one, what is the meaning of this summation? Okay. So I hope the definition of outer measure is clear. Yes or no?
Yes, sir.
Okay. Now let us proceed and see what are all some good qualities that this measure has, outer measure has. Okay. Some properties. So how should I put? Okay. Some properties of Lebesgue outer measure. Mu star or M star. Okay, M star. Certain things will be trivial, but yet it is worth to record. Certain things will be non-trivial. Okay. So first thing, for any A subset of R, do you see that M star of A is greater than or equal to 0? For any A subset of R, the Lebesgue outer measure, which is defined using coverings of open interval, summation of the length, infimum, and so on. Do you see that this will be greater than or equal to 0? Yes or no?
Yes.
Yes, sir.
So
Yes,
I don't
sir.
think
Yes,
I have
sir.
to give a proof for it, right? Because it is infimum of non-negative real numbers. This summation will be non-negative because each L of in is non-negative. Okay, possibly infinity. Now, second property which is trivial is the following. Suppose I take A to be null set, M star of null set. So I want M star of null set. To find M star of anything, first you have to consider a cover consisting of open intervals. Yes, you have to consider a cover consisting of open intervals. And then sum of length of elements in this cover. And then they take different covers and then take the infimum. This is what you have to do. Now, suppose A is null set. What should I do? Can you tell me at least one cover of null set with open
5.
interval?
5.
Null set itself. Null set itself. Okay. And how did you define length of? And null set is defined as an open set, open interval. Remember. And what will be? So it is an cover with a single element, that is null set. So summation will not come into picture, and length of null set is 0. Okay. And then you are taking infimum. If at all you have some other covers, when you are taking infimum, it will be 0 only. So it's not hard to see that M star of null set is 0. Can you see where we are heading to? First thing you see, M star of any A is greater than or equal to 0. Second one, I have recorded that M star of null set is 0. What are these? These are desirable
Properties of
properties
measure.
for a
Measure.
measure. But remember, I have not told what is this corresponding sigma algebra, etc. Okay, those things will come later. Anyway, so these are some properties I would like to record. The next one. Suppose I take a singleton set. Let A is equal to set X, where X is in R. I want to find what is M star of A. What is M star of A? To find M star of anything, first I have to think of a cover consisting of open intervals. And then consider all possible covers and so on. Can you think of one cover containing A, consisting of
Epsilon
open
neighborhood
intervals?
of X.
Pardon?
Epsilon neighborhood of X.
The neighborhood. So can I take X minus 1 by N, X plus 1 by N, for instance?
Yes, sir.
Yeah.
Yes.
Note that for X is here, X minus 1 by N, X plus 1 by N. For each N in N, X minus 1 by N, X plus 1 by N, that is a single open interval. Okay, X minus 1 by N, X plus 1 by N is a cover of set X consisting of open intervals. A single open interval is enough. There is no need for many intervals. So one cover contains one open interval only. So if you have one cover, then what you have to do is to find length of the intervals in that cover. Here there is no intervals, there is only one interval. So sum of length doesn't matter, only length you have to find. And length of this is 1 by 2n, I suppose. And therefore, m star of A is by definition infimum of sum of length in. Okay, as I told you here, the question of sum doesn't arise because in the open cover you have only a single element, namely x minus 1 by n, x plus 1 by n. Okay, and therefore m star of A, which by definition is infimum, is less than or equal to 1 by 2n. You agree or not?
Yes, sir.
Yes. And this is true for each n, for every n in n. Okay. And m star of A is greater than or equal to 0. You already know. So I can put like this, for instance. 0 less than or equal to m star of A is less than or equal to 1 by 2n. Now apply sandwich theorem. As n tending to infinity, if you take m, only possibility is m star of A equal to 0. Therefore, m star of A is equal to 0. So one confusion you may have is why I am not taking summation 1 by 2n. Don't confuse. This is not a single element in the cover. That itself is a cover. X minus 1 by n, x plus 1 by n itself is a cover. Okay. Yeah. So for singleton sets, you have measure to be 0. Next property. Suppose I have a finite set. Suppose A is equal to, we are slightly pushing forward, x1, x2, and so on, xn. Okay. I want to find what is m star of A. You can definitely guess. For a single point, measure is 0, outer measure is 0. If outer measure is going to be a good measure, then measure of A is going to be measure of x1 plus measure of x2 plus so on measure of xn. And measure of x1, x2, xn all are 0. So we should expect that measure of A also as
0.
0.
0.
Okay, but we don't know whether m star is a good measure, whether m star of A will be m star of x1 plus m star of x2. Those things we have not verified. Okay, so but let us now see what is m star of A by the definition. So if you want to find m star of A, I have to first talk about a cover of A containing open intervals. Okay, so let us define cover by open intervals. Yeah, define a sequence in, n belong to n, of open intervals. This union in, if you take, it should cover A, and each in should be open. So what I will do, I1 I will take so that it covers x1. I2 I will take so that it covers x2 and so on. Okay, so I will define define a sequence in of open intervals by in equal to, let us say, xk minus epsilon, or epsilon by 2 you can take, xk plus epsilon, if k is less than or equal to n, and null set if k is greater than n. So this is how I define in. So you have here x1, x2, x3. Let us write it in ascending order, doesn't matter. So this is your I1, This is your I2. I don't mind whether it overlaps or it is disjoint. I don't mind. Okay, like this. And then for k greater than n, null set. Now, do you see that A is contained in union IN?
Yes, sir.
Yes, sir.
Clearly, IN, n belong to n, is a sequence of open intervals that I have already written. Sequence of open intervals that covers A. That covers A. Okay. Now, what should I do to find n star of A? For each of the cover, I have to find summation length and then take the infimum. Right. Now, for this cover, let us first find what is summation. Summation L of IN, n belong to n, would be equal to. So up to IN, the length will be 2 epsilon. Like that, you have n terms, and after that, it is all null set. So am I right to write this as 2 epsilon times n? Yes or no?
Yes, sir.
And this is summation length IN. And what is m star of A? M star of A is infimum of all those things, right? So m star of A will be less than or equal to, by definition, it is infimum of all possible summation length IN where union IN covers A. So m star of A will be less than or equal to 2 epsilon m. Okay, for all epsilon greater than 0. N is fixed. N is number of points. Okay, n is fixed. And epsilon is arbitrary. Now tell me what you can judge from this.
Equals to 0.
0, because epsilon is arbitrary, right? If you wanted to have epsilon, you could have taken, instead of epsilon, you could have worked with epsilon by 2n or whatever it is there. Anyway, since epsilon greater than 0 is arbitrary, don't confuse with this n. This n is fixed number of points in that set. We have m star of A is equal to 0. So for a finite set, measure is outer measure, Lebesgue outer measure is 0. For a singleton set, outer measure is 0. For a finite set, outer measure is 0. Now let us push this forward. 5. Now let us work with a countable set, countably infinite. When I say countable, actually it includes finite as well. So to be precise, I should say either denumerable or I should say countably infinite. Every countable set, whether it is finite or countably infinite, I don't mind. A very countable subset of R has outer measure 0. This is the next property. Outer measure 0. A very countable subset of R has outer measure 0. The idea is already available in the finite set, but let me do it for the sake of completion. Suppose, since it is countable, you can list the elements x1, x2, x3, etc. Either it may stop somewhere or it may be infinite. Is a countable subset of R. Since you have already dealt with finite, maybe you can just assume here it to be countably infinite. Doesn't matter. So now I want to find m star of A. First step is to consider a cover of A consisting of open intervals. Okay. Let epsilon greater than 0. With the idea available in the finite case, can you now tell me which sequence of open intervals I can consider that covers A. Each element in that cover should include one of the points in A. So one interval for including x1, one interval for including x2, like that you can consider. So can you tell me at least one cover consisting of open intervals? How do I define IN? Yes. For each n in n, is it that you don't want to answer or you don't know how to define? Can you hear me?
Sir,
Yes, sir. You can hear it.
So the question is, can you tell me a cover of A consisting of intervals? To
So
cover A,
union n belongings to n.
now I am not talking about union. I want IN. Can you define IN? Then union will cover A. Yeah.
Xn
So
minus epsilon.
So you take xn and I want to include xn in IN. So let us take xn minus what I would say epsilon by let us say 2 power n. You will see why this 2 power n. Xn plus epsilon by 2 power n. This is an open interval containing xn for each n. And therefore, then IN n belong to n is a sequence of open interval. By the very definition, it is a sequence of open interval such that its union covers A. I will write in symbol such that A is contained in union n IN. So you have got one cover consisting of open intervals for A. Now for this cover, what is summation length of IN? Summation length of IN, n belong to n, is equal to summation of length of these things. Summation n belong to n, that will be epsilon by 2 power n minus 1. Am I right? What is the length of this? 2 epsilon by 2 power n, right?
2 epsilon by n. 2 power n.
Yeah. So that will be equal to summation n belong to n epsilon by 2 power n minus 1. Now you should get why I work with epsilon, because I want a convergent series here. And I know that geometric series is convergent. That's the reason why I took epsilon by 2 power n. You could have worked with any epsilon dash. Okay. But finally, I want this to be convergent. That is equal to epsilon times. Can you tell me what this will be? When n is 1, it is 1. So it is 1, I think. Some?
Yes, sir.
Yes,
1,
sir.
2 by 1 minus 1 by 2. A by 1 minus R. So anyway, it is epsilon. So summation n belong to n, length of IN is epsilon. Okay. So for a particular cover consisting of open interval, summation length of IN is epsilon. Therefore, M star of A, which is by definition infimum of all such quantity, which is infimum. Let me write so that you can recall once again the definition. Infimum of some length IN, where INs are intervals, open intervals, and A is contained in union and IN. This is the definition. Since it is by definition infimum and one of them becomes epsilon, M star will be less than or equal to epsilon. And epsilon is arbitrary. Since epsilon greater than 0 is arbitrary, we have outer measure, Lebesgue outer measure for a countable set A is 0. Finite or countably infinite, the outer measure is 0. Okay. In particular, what will be measure of Q? Note, in particular, outer measure M star of Q, the set of all rational, will be 0. Yes or no?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
So this will indicate that outer measure has some good property that we want any reasonable notion of measure to possess, because Q is something like infinite number are there, but it has fewer in number compared to the other real numbers. So there are fewer rationals than real. Therefore, this M star of Q equal to 0 is something like meeting our expectation. If the set has fewer elements, then its measure is 0. The countable sets has measure 0. So this is a good sign that M star has some desirable property that we expect. Now, let me say another desirable property that, or another good property that M star has. Suppose you take two different subsets of R, A and B, such that one is contained in the other. Let A and B be two subsets of R such that A is contained in B. I wanted to compare what will be M star of A and M star of B. Natural expectation is M star of A should be less than or equal to M star of B. Then M star of A is less than or equal to M star of B. Again, M star meets our expectation. This is M star is monotonic. We say that is M star, Lebesgue outer measure, is monotonic. Monotonicity of Lebesgue measure. That's what we wanted. Outer measure. That's what we wanted to prove now. Okay. Now, if you want to talk about M star A, M star B, etc., the starting point is the cover consisting of open intervals. So let us take a cover consisting of open intervals for the set B. Okay. So I am going to prove this. Okay. Let n belong to n be a sequence of open intervals that's the starting point for outer measure, open intervals that covers B. That is, what do you mean by covers B? That is, B is equal to union n in, n belong to n. B not equal to, B is contained in. Okay, so I have started with an open, I will not call open cover, cover consisting of open intervals for B. Okay. Now, do you see that this will automatically cover A as well?
Yes, sir.
Yeah, because B, A is contained in B, right? Then A is contained in B is contained in union n element of In. So any cover consisting of open intervals for B is automatically a cover consisting of open intervals for A. Okay. And therefore, M star of A, by definition, it is infimum, will be less than or equal to summation n belonging to n L of In. Yes or no?
Yes, sir.
Yes, sir.
And what is In? In is an arbitrary sequence of open interval that covers B. That means this inequality is true for any cover of B consisting of open interval. So once it is true for any cover, you can take the infimum. Okay, taking infimum over all sequences of open intervals whose union covers B. We get M star of A is less than or equal to infimum of summation n belong to n L of in's open intervals, and B is contained in union n in. This by definition, what you have on the right hand side is M star B. This is M star B. Thus, M star of A is less than or equal to M star of B. This proves the monotonicity of Lebesgue outer measure. Larger the set, larger the measure is, as one should expect. Now, before going to the next property, let me introduce a notation. Translation of a set. Let A be a subset of R and Y belong to R be fixed. In R, you have an addition. So now I am going to define Y plus A. Y plus the subset A. As you can expect, the natural definition would be Y plus small a where A belong to A. Define Y plus A like this. Called translation of set A. Okay, this is just for notation. I have introduced what is a real number plus a set, a subset of R. Now, suppose your A is an interval. Let us say open interval. Let A is equal to open interval AB. Can you say what will be Y plus A? All the points in A will get translated by the quantity Y. So what will be finally Y plus A? It will be again an open interval, right? Y plus A, Y plus B. Do you agree?
Yes, sir.
Yes.
Now
Yes,
what
sir.
length of Y plus A?
B minus.
B minus A.
Then,
Is it same as length of A?
yes, sir.
Yeah.
Yes, sir.
So translation of open intervals keeps the length unaltered. Length of a open interval and its translated version is same. Now, a natural expectation is whether this will be true for your M star, because M star is a generalized version of length. So the question that we want to pose is whether M star of A will coincide with M star of Y plus A for all Y in R. Whether M star is translation invariant, and answer is yes. Okay. So that is the next property. 7. Lebesgue countermeasure. So the property that you have for length and open interval get pushed forward to measure, outer measure and sets as far as translation is concerned. Lebesgue countermeasure is translation invariant. That is M star of y plus a is same as M star of a for every a subset of R and y belongs to R. Something like you find volume of a sphere in this room, travel, go to the next room and find volume of the sphere. It will remain the same. So this is actually the rigid body motion, right? Anyway, so outer measure has some desirable properties that we expect. One of them is translation invariant. Now, how do you prove it? Proof. So I would start with an open cover of A consisting of open intervals. Suppose I1, I2, etc. Why should I write like this? I will write IN, sequence IN. Suppose sequence IN, N belong to N, be a sequence of open intervals that covers A. What do you mean by that? Covers A? That is, A is contained in union and IN. To be more precise, I should say open intervals whose union covers A. That will be the more precise. Whose union covers A. So A is contained in union and IN. That's the meaning. Okay. So can you get an open cover consisting of open interval for y plus a from this? Can you get a sequence of open interval?
So translation of
right?
each IN.
Translation of each IN. Then the sequence y plus IN, n belong to n, is a sequence of open intervals whose union covers the translated set y plus a. Okay, and therefore m star of the translate version y plus a is, by definition, it is infimum of all such sequences of open intervals. I mean, infimum of summation length and so on. So this is less than or equal to summation n length of y plus in, because by definition m star of is infimum of such quantities. Okay, and this is summation over n length of in. Okay, and this is true for any sequence of open interval whose union covers A. So now take infimum. Taking the infimum, over all such sequences. Such sequences means sequences of open intervals whose union covers A. We get m star of y plus a is less than or equal to infimum of such quantities, which is m star of a. Okay, let me name it as 1. But we want to prove that m star is translation invariant. We want to prove the equality. You have proved only one way. Now, without doing an independent proof for the reverse inequality, can you derive it from what you proved already? Now I wanted to say m star of A is less than or equal to m star of y plus A. Can I say this? See, what you have proved is if you have A, then its translated version y plus A will have measure less than or equal to the original. The translated version will have measure less than or equal to original. Now I want to get the reverse inequality. Can I get A from y plus A by translation?
By translation,
Yes,
y
sir.
minus y.
Yes, sir.
Yeah, how? Take minus y, right? So note that I want to recover A from y plus A by translation. Note that A is y plus A plus the number minus y. So this plays the role of A in the previous proof, and this plays the role of y. This is minus y play the role of y, and y plus A play the role of A. Okay. By what we proved already, m star of A, which is equal to m star of minus y plus A, and m star of a translation is less than or equal to m star of the original. You already proved. Original is here y plus A. Okay. This I will name as 2. Combining 1 and 2. We have outer measure of a set. Lebesgue outer measure of a set is same as Lebesgue outer measure of its translated version, y plus A. Whether you measure now or you measure after y amount of time, doesn't matter. It remains the same. Next, one more desirable property, one more good property of a outer measure, of a Lebesgue outer measure. Let me put it as a theorem. Outer measure of closed interval, what it will be? The outer measure, to be precise, Lebesgue outer measure of an interval I is equal to AB, where A and B are real numbers, A less than B. We are talking about only finite intervals, closed bounded intervals. The outer measure of an interval I equal to AB is m star of AB. What is your expectation?
Equals to measure of open interval.
That is B minus A, length, right? The measure of the closed interval is equal to the length. See, our aim was to get a measure consistent with the length. And length is defined not only for open interval, it is defined for any interval. So finally, we should get m star of any interval you take should be equal to length of the interval. Okay, we will reach it at that level. Now we are proving only for a closed bounded interval. M star of AB is equal to B minus A. I will not prove this today. We will postpone to the next lecture. One part is very straightforward. To prove that M star of AB equal to B minus A, I have to prove that I will prove that M star of AB is less than or equal to B minus A, and it is greater than or equal to B minus A. So two inequality I will prove. Okay. And proving M star of closed bounded interval AB is less than or equal to B minus A is trivial. Now you want to prove M star of something. You want to look at M star of something. First, I need a sequence of open interval whose union covers AB. Yes or no?
Yes, sir.
Can you tell me a sequence of open interval that covers AB?
A minus epsilon, comma B plus epsilon.
A minus I1 you take as open interval A minus epsilon, A plus B plus epsilon. I2, I3, I4, etc. you take as null set. Then you will get a sequence of open intervals whose union covers I. Okay. And now you find length of those. Length of that will be B minus A plus epsilon. Yes or no?
Yes, sir.
Yes, sir.
B A minus epsilon B plus epsilon. This is my I1. I2, I3, I4, etc. I will take as null set. Okay. Now length of I1 is 2 epsilon. B minus A plus 2 epsilon. Okay. So sum of the length will be B minus A plus 2 epsilon. By definition, M star of closed interval AB is infimum. Therefore, M star of AB will be less than or equal to B minus A plus 2 epsilon. And it is true for all epsilon. And therefore, you will get M star of AB is less than or equal to B minus A. So that part is going to be trivial. But the other part is bit involved. Okay. You have to work with intervals that covers AB, open intervals, countable. Okay. From countable, I will go for finite because it is more easy to work with. And fortunately, in the case of closed bounded interval AB, I can do that. There we invoke so-called Henneborel theorem. What is Henneborel theorem says? A closed bounded interval is compact. So every open cover will have a, I don't know whether you know,
Finite subcover.
Finite
finite
subcover.
cover. So given any sequence of open interval countable whose union covers AB, I can extract a finite subcover and then I have to work only with the finite. So in the converse part, the Henneborel theorem will play a crucial role. So that's how we are going to prove this theorem. Anyway, the detail I will leave to the next lecture. I will reserve for the next lecture. So what today we did is we defined what is Lebesgue countermeasure and we established some nice properties of it. We will proceed with it, but don't expect too much. Lebesgue countermeasure doesn't have all the properties that you expect for a measure. Okay. That you will see. With that, let me stop. Thank you.